Welcome to Concept in Medicine. In today's session, we'll be looking at the pressure volume loop. My name is Dr. Del. Let's begin by looking at the pressure volume loop diagram. So the first thing we are talking about is that the axis. We have the y-axis and the x-axis. The y-axis represents the pressure, whilst the x-axis represents the volume. It represents the volume. Now on this diagram, we are going to label the diagram, and after that, we'll be explaining what each and every representation means. So we'll start with point one. At point one, you are going to have the mitral valve opening. Point two, you have the mitral valve closing. Now, how do we easily understand why the mitral valve is at the bottom? Then that tells you that if you take the heart, right, the chambers, here we are going to have right atrium, right ventricle, left atrium, left ventricle. Between the right atrium and the right ventricle, you're having the tricuspid valve. Between the left atrium and the left ventricle, you're having the mitral valve. Now, if you watch this very carefully, the mitral valve is located where? In the mitral area. Where is that? You're having the fifth intercostal space, left mid-clavicular line. Now, you're asking yourself, where is the tricuspid valve? It is going to be the fourth intercostal space, left lower sternal border. That is in the parasternal line. So if you watch all this, you realize that these and these, they are located in the lower region as compared to the aortic valve and the pulmonary valve, which are located in the second intercostal space. To the right, you have the aortic valve, and to the left, you have the pulmonary valve. So the mitral valve will always be lower than the aortic valve in this scenario. So we are saying that at point one, the mitral valve will open. Why does it have to open? It has to open to allow blood to move from the left atrium into what? The left ventricle. Okay? And this will be happening during diastole. During diastole, because it's during diastole that the mitral valve will open. The next one is 2. At point 2, the mitral valve will close. The moment the mitral valve closes, it signifies the end of diastole. The moment the mitral valve opens, it signifies the beginning of diastole. Once it closes, end of diastole. And the end of diastole corresponds to what? The beginning of what? Systole. So, beginning of systole, end of diastole, we are going to have what? End diastolic volume. The beginning of diastole signifies the end of what? Systole. So here we are going to have the end systolic volume. That is why, if you look at C, it is what? The end systolic volume. If you look at D, it's the end diastolic volume. Okay? Now, at the beginning of systole, the mitral valve closes, and within some few seconds, the aortic valve would what? Open. That is why at 3, you're having what? Aortic valve opening. And why does the aortic valve needs to open? It needs to open so that the left ventricle can push blood through it into the systemic what? Circulation. So here you are going to have the aortic valve what? Opening. And this is going to be in systole. Now when the aortic valve opens, what does the left ventricle need to do? It needs to what? Contract. And as it contracts, what does it do? It ejects a volume of blood from each chambers into the systemic circulation via the aorta. And that volume of blood that is ejecting per heartbeat, we will call it what? The stroke volume. And again, that volume of blood, it is ejecting out of the total amount of blood in each chambers at the end of diastole, which we call the end diastolic volume. We'll refer to this as what? The ejection fraction. So if you look at this trajectory, it's showing that there's an ejection ongoing. So if you are ejecting, it follows what? A curve. That is why this is a curve. So this is an ejected what? Volume. And if the left ventricle is contracting to eject blood through the aorta, it is going to face a resistance in the aorta, which is an artery. And that resistance, we'll refer to it as what? The afterload. So that is why F is referred as what? The afterload. So it means that the left ventricle needs to contract so much so that it can push out the volume of blood in the left ventricle at the end of systole, which we call the end diastolic volume, or preferentially the preload. It needs to push this volume out of each chambers into the systemic circulation via the aorta. That is why the aorta is opening. And when it does that, it's going to meet a resistance we call what? The afterload. So the height of this curve determines what? The afterload. If the height of the curve is increasing, it means the afterload is high. If it is decreasing, it means the afterload is what? Low. Now, if the left ventricle finished ejecting this volume of blood, work done. So what is going to be done next? The aortic valve needs to what? Close. That is why at 4 we are having the aortic valve what? Closing. The moment the aortic valve closes, it means systole is done. So here we are having end of what? Systole. And that means beginning of what? Diastole. So if you watch very well, this line here, line that you're having here, it's referencing the starting point of diastole with respect to the mitral valve and with respect to what? The aortic what? Valve. So this is the beginning of diastole with reference to what? The aortic valve. And what do we have here? This is the beginning of what? Diastole again with respect to what? The mitral valve. So if you watch very carefully, when the left ventricle is contracting, the volume that is in the left ventricle at the end of diastole does not change because the mitral valve has what? Closed. Once that volume is the same, when it's contracting, then we'll say that the volume is not changing, it is equal, and the contraction is taking place. We refer to that, this line here you are seeing here, we call it what? An isovolemic contraction, because that is during systole. Now, the next one, if you come here, beginning of diastole, we are looking at beginning of diastole with respect to the mitral valve and with respect to what? The aortic valve. So here, the volume does not change again. What are we going to have? We have isovolemic relaxation, because when you are in diastole, the ventricles will what? Relax, so that blood can fill their chamber as a result of a decreased pressure in them and what? An elevated pressure in the atria due to what? Blood accumulating in the atria. Now, once you have that, we are saying that once you have the mitral valve opening at 1 and closing at what? 2, the opening at 1 means the end of what? Systole. So the volume that is there, we call it end systolic volume. And the closure of the mitral valve signifies what? The end of the diastole. So the volume at the end of diastole, we call it what? End diastolic volume. Now, the difference between the end diastolic volume and the end systolic volume would give us what we call the stroke volume. The stroke volume. And that is indicated by the length of what? This line. The length of this line that you have here, which is represented as E. Now, how do we know that the end systolic volume is decreasing or increasing? The end systolic volume is decreasing when it's moving towards what? The left. And if it's moving towards the right, it is increasing. The end diastolic volume is increasing when it's moving towards the right, and it's decreasing when it's moving towards what? The left. The afterload, which is F, is increasing when the height of the curve is rising, and it's decreasing when the height of the curve is lowering. Once we are having this line shifting to the left, it means that the preload has decreased. If we were to shift to the right, it means it has what? Increased. Now, this, which is B, we call it contractility. Contractility. The contractility increases when this point here, this corner here, is moving towards the left. It is increasing when the point, this point here, is moving towards the left, and it's decreasing when this point is moving towards the right. Now, with that being said, we also have what we call the compliance. Compliance. The compliance would increase when the end diastolic volume is shifting. Because when there's increase in the volume of blood in the left ventricle, what do you expect the left ventricle to do? It's supposed to stretch. So the ability to stretch or dilate in response to an increasing end diastolic volume, we call it what? Compliance. With that being said, that would indicate or describe this pressure volume loop. Let's move on to look at some examples of the pressure volume loop and also give interpretation or observations with regards to examples. So we'll start with the first one. That is going to be this pressure volume loop. What the thick lines, the one that is continuous, are the physiological pressure loops. Then the dotted ones are changes after certain conditions or interventions. So you have this, when you have this pressure loop, you look at it very well physiologically. We know that this is afterload. This is what? Preload. We know that this is N diastolic volume. This is N systolic volume. And the length of this line becomes what? Stroke volume. We know that. We know that this is contractility as well. Right? Now, if you observe this very well, you realize that the change, which is in the dotted, you realize that the afterload here is what? Increased. Afterload is increased. What are we having with our preload? Our preload is also what? Increased. Now, if you watch the stroke volume, the end systolic volume has moved from its original point here, it has increased, and the end diastolic volume has also increased. So if you look at that, both increasing, it means that the stroke volume would be what? Normal, or maybe what? Slightly increased. Depending on the magnitude of increase. Because if both are increasing, then meaning that physiologically, they are balancing. Because if I increase, the difference will be the same. So you see that the afterload is increasing, which is here. The preload, which is here, has increased to this point. Then the stroke volume, since there's an increase in both end systolic and end diastolic volume, the stroke volume will remain what? The same. And the compliance will be intact. Okay? And the preload and the afterload increasing seeks to what? Comply with the Frank Starlings in a way, but it's not fully complied because the stroke volume has not what? Changed. So that one, the Frank Starling law is not what? Working. Okay? So that's the interpretation for this. So you ask yourself, which condition can increase, or which intervention can increase the afterload? That is the resistance to what? The blood flow, and increase what? The preload. But the stroke volume is not enough. Then you ask yourself, the afterload, it means that if it's increasing, then it means there could be a left ventricular outflow tract obstruction. The preload, if it's increasing, then it tells you that you could have the myocardium, the left ventricular myocardium, not being able to what? Contract adequately. And if it's not being able to contract adequately, it means that the left ventricle may be failing. It may be failing due to several reasons. So that will be the interpretation for this. Afterload increasing, preload increasing, stroke volume, since end systolic volume and end diastolic volume are both increasing, it will be what? Almost the same. Now the second one, who would tell us? Okay, so let me give you that.
Okay, so the afterload is increased. The preload is also increased. And the stroke volume is increased as well.
Okay, so as you said that the afterload is increased, which we are witnessing here. The afterload is increased. The preload, which we are witnessing here, is also what? Increased. The stroke volume is increased because the end systolic volume remained the same, but the end diastolic volume what? Increased. So when you find the difference, what are we going to have? An increased what? Stroke volume. So that is correct. But if you watch this very carefully, the afterload is not significantly, it's not so high. It's slightly increased. It's slightly increased. If you compare this and this, you realize that the afterload here is significantly increased. Here, even though it's increased, it's not as high as compared to what? This one. So that is correct. The next one, who will tell us?
The end systolic volume decreases. The preload is the same. The afterload increases.
Is it significant? Is it that high or slight?
It's significant. The stroke volume increases.
Take that again.
The stroke volume increases.
Why is it increasing?
Because the end systolic volume has decreased, yes. And then also the contractility has increased.
For this graph, as you rightly said, the end systolic volume is decreasing because it has moved from its original point towards the left, so it has decreased. The end diastolic volume remains the same, and we know that the stroke volume is the difference between the end diastolic volume minus the end systolic volume. Hence, once this is decreasing, then it means that the stroke volume will increase. So that's what you're having there. The stroke volume is increased, the end systolic volume will decrease. Look at the preload. The preload is here. As you can see, the preload has not changed. It's still the same. So that's what we are having there. Now we go to the afterload. The afterload, look, this curve, it has increased slightly. So we'll say that the afterload is what? Slightly increased. The stroke volume, we already talked about that. Then the contractility. If the afterload is increasing, then it means that the contractility will also have to what? Increase to balance the equation. So the contractility here is what? Increased as well. Now let's move to the fourth one. Okay.
So for the fourth one, the preload will decrease Afterload will be decreased also slightly. End diastolic volume will also be decreased, whilst the end systolic volume will remain the same. So meaning that the stroke volume will be decreased.
Once we are having this line shifting to the left, it means that the preload has decreased. If we were to shift to the right, it means it has what? Increased. So in this case, we say our preload is what? Decreasing. The afterload has seen a slight decrease. So the afterload is what? Slightly decreased. The end diastolic volume has shifted to the left, meaning that it's what? Decreased. The end systolic volume is still the same, meaning our stroke volume is what? Reduced. Who is telling us the last one?
The preload will be decreased. The end diastolic volume also decreases. The end systolic volume decreases. The afterload decreases. Then the stroke volume will also reduce. So the decrease in the end diastolic volume is more than the decrease in the end systolic volume. Hence, there will be a decrease in the stroke volume.
So, yes, as you rightly indicated, the preload is what? Decreased. Because if you look at the height, this one is lowered. The afterload is also decreased, as you rightly said. The end systolic volume, there's a minimal decrease in it. The end diastolic volume, there's a significant decrease in it. And we know that the difference between the end diastolic volume and the end systolic volume will give you the stroke volume. Meaning, once there's more decrease in the end diastolic volume, there's going to be a decrease in the stroke volume. And that is accurate. So, it shows that the concept has been retained and the audience have been useful with regards to answering all the questions that has been put across the board. I am glad that the concept has been retained. Thank you very much for joining in the lesson. It's been a great lesson. Kindly make sure to subscribe to my channel, like, share, and also recommend to friends. My name is Dr. Del, and this is Concept in Medicine. Bye-bye.